Good day, grade 12 learners. Welcome to today's technical science lesson. My name is Musa Zulu. This lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. All right, grade 12. Today, our knowledge area of focus, we're going to be focusing on matter and material, as has been the case for the past few weeks. And our topic for today is going to be electronic properties of matter. So we're going to be focusing on electronic properties of matter as a topic today. A very, very small topic for our case. It's a very, very small topic that we're going to just look at it today, and we should be finishing everything today. More specifically, we're going to be focusing on semiconductors when it comes to electronic properties of matter. We're going to be focusing more on semiconductors. Right. So our lesson objectives for today is that by the end of the lesson, we must be able to, one, we must be able to define a semiconductor. Two, we must be able to define an intrinsic semiconductor and doping. So we must be able to define an intrinsic semiconductor, and we must be able to define doping. And number three, we must be able to differentiate between an N-type and a P-type semiconductor. We must be able to explain the construction and working of a PN junction diode, and we must be able to interpret the characteristics of a PN junction diode. So those are the things that we are expected to know by the end of this lesson. Okay, what knowledge should we come to this lesson with? What are the things that we should be able to remember, things that we have learned previously? Well, we must be able to define what a conductor is. We must be able to define an insulator. These are things that we learned in previous grades, more specifically in grade 10. We define a conductor, we define an insulator. We must be able to identify in the periodic elements in the periodic table of elements by using groups to say, can you identify elements in group 3? Can you identify elements in group 6 in the periodic table? And then we must be able to explain the term valency, another term that was introduced to us in grade 10. Again, when we were doing semiconductors there, we were expected to explain the term valency. We must be able to identify the valency of an atom by using groups in the periodic table. So this issue of knowing groups in the periodic table becomes very, very important, because we must be able to identify elements using groups. We must also be able to identify the valency of an atom, again by using groups in the periodic table of elements. Okay, so let's look at just quick questions that are going to help us remember these things that we've just talked about. So we can look at questions like define a conductor, and then number 2, define an insulator. Give any two elements in group 3 or 4 and 5. So looking into your periodic table of elements, and I want you to look at group 3, group 4, and 5, and give just any two elements that you can find there. Explain what is meant by the term valency. So what you understand by the term valency, what is meant by that term. And number 5, give the valency of sulfur, nitrogen, and arsenic. Okay, right. So just to quickly and save time, the solution to those questions would be a conductor is a material that allows electricity to flow through it. A conductor is a material that allows electricity to flow through it. Most of the times, these in our periodic table are metals. Metals are usually conductors. They allow electricity, or they allow electricity to flow through it. While an insulator is a material that does not allow electricity to flow through it. Usually in our periodic table, we'll identify these as non-metals. And this is what we did when we were talking in grade 10. We said we have metals that are usually conductors. We have metals that are usually conductors. We have non-metals that are usually insulators. Okay, then we said give elements in group 3, group 4, and group 5. Well, then these are the elements that you can find in group 3. We said any. These are the ones I chose: gallium and aluminium. Elements that you are going to find them in group 4, you will find carbon and tin, right? It's just any two. And elements that you will find in group 5 are nitrogen and phosphorus, right? Now, all the elements in that column, all elements in the column where nitrogen is, those elements are elements in group 5. All elements in the column where carbon is, those are elements in group 4. And all elements in the column where gallium and aluminum are, those are the elements in group 3. It's important for us to be able to identify that in our periodic table of elements. Okay, and then the next solution or the answer to the question was for us to explain what is meant by the term valency. Well, the term valency tells us the number of chemical bonds an atom of an element can form. How many chemical bonds an atom of an element can form? That's valency. Okay, well, other people, they would say valency is the number of electrons in the outermost shell. If you understand it like that, it is also fine. Valency is the number of electrons in the outermost shell, to say how many electrons are in the outermost shell. Then how do we then combine this with the knowledge of groups in the periodic table? Well, for example, if we look at carbon and we say carbon is in group 4, then we would say carbon has carbon is able to form 4 chemical bonds. You should remember this again. It's what we've been talking about when we were doing organic chemistry. Carbon is happy when carbon has 4 bonds. So carbon is able to 4 bonds. So the valency of carbon is then 4. Okay. Then a question was asked there to say, what is the valency of sulfur, nitrogen, and arsenic? The valency of sulfur is 6. And again, if you go and look at sulfur, in what group do you find sulfur? You find sulfur in group 6. So its valency is 6. It's able to form 6 bonds, right? And then nitrogen, its valency is 5. You will also find nitrogen in group 5. Arsenic is also found in group 5. Again, its valency is 5. Its group number is 5. So by knowing the group number of a certain element, then you can tell its valency. That is going to be important moving forward, grade 12. All right. What is our terminology for the day? Things that we must be able to say, or certain words that might be new to us. Number 1, semiconductors, which is what we're going to be focusing on. And we say semiconductors are defined as material that has the electrical conductivity between that of a conductor and an insulator. And this is very, very important in grade 12 to understand that a conductor is the material that allows electricity to flow through it. An insulator is the material that does not allow electricity to flow through it. But a semiconductor is a material that has the electrical conductivity between that of a conductor and of an insulator. We must know an intrinsic semiconductor that we must know as a pure semiconductor. So when we talk of intrinsic semiconductor, we say it's a pure semiconductor. So we just use those words, we remove the pure and we just use intrinsic. So it's intrinsic, it means it's pure. It's a semiconductor that consists only of itself. Doping is another new word there, process of adding impurities to intrinsic semiconductors. And then N-type semiconductor, these are semiconductors where electrons are charge carriers. So in N-type semiconductors, we say electrons are charge carriers there. P-type semiconductor, semiconductors doped with acceptor impurities that end up creating holes. Okay, this will make sense in just a minute. Right? Trivalent, the word trivalent there, if you can check here, there are 2 words that have been combined here, tri and valent. And we've just spoken of valency. Tri from organic chemistry again, tri means 3. So when you say trivalent, this should mean it's a valency of 3. So it means that atom has a valency of 3. It is trivalent. So instead of saying a valency of 3, another word that can be used there is trivalent. A word that you should familiarize yourself with so that when you see it, you are not shocked. And then another one is pentavalent. Pentavalent, again, it's pent 5. If you remember there, pent was 5 when we were doing organic chemistry. Valent from the word valency. So pentavalent, that should mean having a valency of 5. So it's important to understand what valency is, so that when we talk of words like trivalent, something is trivalent, an atom is trivalent, or it's pentavalent, these words are not confusing you at all. Okay, as we continue with our terminology, we will also be introduced to a word diode. This is a device that allows current to flow only in one direction. A device that allows current to flow in one direction. We will also be introduced to forward bias. What does forward bias? This is a setup where the p-type is attached to the positive terminal and the n-type is attached to the negative terminal. Things that will make sense in a couple of minutes. Reverse bias, setup where a p-type is attached to a negative terminal and an n-type is attached to a positive terminal. We say that's reverse bias. And then anode, a positive terminal of the diode. So anode is a positive terminal of the diode, while cathode is the negative terminal of a diode. So those are the ways that by the end of this lesson, we should be able to know what they mean and be familiar with. All right. So I want to go back grade 12 to where we started. We said we must be able to know what a conductor is and what an insulator is before we can even jump to a semiconductor. So before I even talk of semiconductors here, so I want you to understand what is happening here. So we have a conductor. We say a conductor is a material that allows electricity to flow through it. So, right, usually metals, okay? That's good. We have a conductor. It allows electricity to flow through it. So that's good for us. And then we have an insulator. These are usually non-metals. These ones, they do not allow electricity to flow through it. And then we have a semiconductor. Okay, what is a semiconductor? We say this is a material that has the electrical conductivity between that of a conductor and an insulator. Well, just right there, having the electrical conductivity that is between, is good for us. Okay, if you were to take a semiconductor and you were to connect the semiconductor on a circuit, right? You connect a semiconductor on a circuit, right? Chances are that semiconductor is not going to allow electrons to pass through it or electricity to flow, right? Now, can we then say that semiconductor is not a conductor or will not be able to conduct electricity? Well, the answer to the question is no, okay? Because as it says, it has the electrical conductivity that is between. So what does that mean? That means we can do something to a semiconductor that will make a semiconductor to conduct. Unlike an insulator is not going to conduct electricity, not going to do anything that will cause an insulator to conduct electricity. If you remember, this conversation was had in grade 10. Okay, a conductor is good. Where good is conduct electricity, there is nothing more we can do about it. It's good for us. However, a semiconductor appears as if it cannot conduct electricity, but there's certain things that you can do to it that will conduct electricity. Like what? In grade 10, we say, if you take a semiconductor and you increase temperature on a semiconductor, this will excite the electrons and the electrons will start conducting electricity. That was in grade 10. We say, we can increase the temperature on the semiconductor itself. Then it will do what? It will start conducting electricity. That's why they say it has the electrical conductivity that is between. That means depending on what you do on the semiconductor, you might find the semiconductor conducting electricity, but you might find the semiconductors not conducting electricity. So whatever you do to the semiconductor will determine whether it will conduct or it will not. So it has the electrical conductivity that is between that of a conductor and an insulator. And in grade 10, we learned that we can increase the temperature on the semiconductor and the semiconductor will conduct electricity. That's important. Right, before we move on, here are the following examples of naturally occurring semiconductors. Right, these ones are found here in group 4 there: carbon, silicon, germanium, and also gray and alpha tin. Okay, the material usually there would be diamond, silicon, germanium, gray tin, alpha tin. Okay, the semiconductors that we are going to be using the most grade 12 will be silicon, and sometimes you might find germanium being used, but my example for the day will be based around silicon as our semiconductor. We are trying to do something to silicon to make silicon conduct electricity. So that's the idea of today's lesson. Silicon does not just conduct electricity when I connect it into my circuit. However, I believe I can do something to silicon and make it conduct electricity. So that's what I want to find out. What can I do? to silicon. I can increase the temperature of silicon. That's what happened in grade 10. But is there something else that I can do? Before we jump into that, we need to have an understanding of an intrinsic semiconductor. What do we call an intrinsic semiconductor? An intrinsic semiconductor is a pure semiconductor. What is a pure semiconductor? This is a semiconductor that only consists only of itself. Remember in our example, we said silicon is an example of a semiconductor. So I'm going to use silicon here, right? Here is silicon. Silicon here is only bonded to other silicon atoms. So this is the silicon crystal here, only bonded to other silicon atoms, okay? So it is pure because it has nothing else that is not silicon. It only consists of itself. So it's a pure semiconductor. We call it an intrinsic semiconductor. As we say here, this means a semiconductor that only consists only of atoms, all right, of itself. And these atoms are covalently bonded to each other. As you can see here, we have this atom or electron coming from this silicon and this one coming from the other silicon, and they have created now a covalent bond. So we have covalent bonds here between all these silicons, and everything here is stable, right? Why are we saying everything here is stable? Well, if you look at silicon, each and every silicon here has 4 bonds around itself, or ultimately 8 electrons, as was the discussion in grade 10 again, to say atoms are usually stable when they have 8 electrons. So with this silicon sharing other electrons with this electron, it ends up having 8 electrons, this one having 8 electrons, and everything here is stable. And this is the reason why if I were to simply connect this silicon into a power source of some sort, this silicon is not going to conduct electricity because everything here is stable. There's no need for these electrons to move, right? They don't see the need to move. Everything is stable. They've shared electrons equally and everyone has 8 electrons. Everyone is happy here. So this is what we call an intrinsic semiconductor. This semiconductor is pure, and this semiconductor is not going to do what? Conduct electricity for us. It's at a point where it is an insulator, because remember there's the electrical conductivity between that of a conductor and an insulator. So at this point, it's at the side of an insulator, okay? Until I do something to it again. What can I do to silicon, or what can I do to a semiconductor to make it conduct electricity? I can do something called doping, okay? What is doping? Doping here means the same thing as you usually hear of it. I'm sure out there, grade 12, you've heard of the word doping. Where do you usually hear of the word doping? Do you usually hear of the word doping in sporting activities, for athletes, for footballers, for rugby players, right? You find that a player has been banned for a couple of weeks, and they ask you why was the player banned, and the answer to the question is that the player has been found to be doping. Okay, what does it mean that the player was doping? It means the player has used other substances, right, coming from outside, and the player has used them to enhance his or her ability to perform. So doping here means exactly the same thing, or is used in the same sense. We are adding impurities to an intrinsic semiconductor, and we want to enhance this semiconductor. We want this semiconductor to start conducting electricity because it was not conducting electricity. So what do we do to it? We dope it. We add impurities. So it's a process of adding impurities to an intrinsic. You'd remember an intrinsic semiconductor, this one. We said this one is not going to conduct electricity. It's intrinsic, it's pure, everything is stable. It will only do that if I just simply do what? Add impurities. So if I can add impurities on this intrinsic semiconductor, this semiconductor should start conducting electricity. Okay, so how do I do this doping? I can dope by adding impurities. What impurities? These impurities will be elements that I get from group 3. those elements are trivalent. Remember that, you know? Elements that I find in group 3. So this would be my periodic table of elements. I've taken only the part that is needed for this section, grade 12. The periodic table obviously is not this much, right? But the elements that are in group 3 would be these elements, okay? These are the elements that I can use to dope a pure semiconductor like silicon and try to make it conduct electricity, okay? Or I can also dope by using elements in group 5. What elements are in group 5? This is group 5. These are the elements that are found in group 5. I can use these elements again to dope an intrinsic semiconductor, or use them as an impurity, adding to an intrinsic semiconductor and try to make this semiconductor to conduct electricity. Okay, so let's try and see if we can do this doping and check if we understand what we are talking about here. Okay, so how are we going to do this doping, right? Let's say we have silicon. Okay, here's silicon, here's another silicon, here's another silicon, here's another silicon. Okay, let's say we used to have another silicon here. Okay, I want to explain what is happening here so that you will understand. So we used to have another silicon here. It was a pure semiconductor, an intrinsic semiconductor. Now we are deciding to dope it, meaning we are deciding to introduce or add impurities to enhance this silicon, to enhance its performance, like the way doping is used in our everyday lives. What can we do? We can take an element from group 3, such as aluminium. So we take an element from group 3, such as aluminium, and say, let's add an impurity here, such as aluminium. Now you remember that each silicon has a valency of 4, meaning that it comes with 4 electrons in its outermost shell, or the bonding electrons. They are 4. However, when you look at aluminium, aluminium is going to bring in 3, only 3 electrons. Okay, so that means, as you can see here, this silicon here is going to form a covalent bond here. This silicon will also form another covalent bond here. This silicon will form another covalent bond here. But here, it will not be able to form a covalent bond. Why? Because for a covalent bond to be formed, we need a sharing of 2 electrons. If you remember when we were doing again organic chemistry, for a covalent bond to be formed, we need to share, 2 atoms need to share 2 electrons. Now here, it is incomplete because this electron is not there. Remember, aluminum only brought 3 electrons to this part here. So we end up having a hole here, a space that aluminum is bringing. So as it says here, there's a presence of a what? Of a hole, right? Now this is important, grade 12, because now if you remember, one of the reason why this silicon was not conducting here, this one here, which was pure, one of the reasons why this one was not conducting is because everything was stable. Everyone had 8 electrons around him or herself. Everyone was happy. But now, if you now go to this one, and I have added an impurity such as aluminium coming here to add impurity, now you realize that now this silicon is no longer going to be happy. Why? There's no one to share an electron with. All the electrons of aluminum that aluminum brought have been taken by other silicon. Now there's the presence of the hole. We have put an instability in this situation. This situation is now unstable. Not everyone is happy. Okay? And this hole turns out, grade 12, that this hole brings a positive charge. We say it is a positive charge carrier. It carries positive charges. This is another thing with this hole. It's going to carry a positive charge. It's a positive charge carrier. Again, bringing more instability into the situation. Because now, if you remember with electrons, electrons are negatively charged. Okay? If this hole carries a positive charge, now we might have a problem here, right? Because what this is going to do, it will now start attracting electrons from the silicon crystal itself, because it's positive. Remember, unlike charges attract. So it will then start attracting these charges, which are electrons, meaning that it might be this electron being attracted here. And remember, when this electron is attracted here, it must leave a hole there, meaning that another electron from somewhere else will be attracted as well. So there's going to be this movement of electrons being attracted to these holes that are carrying positive charges. In that case, we are having a movement of electrons. And what is a movement of electrons? That is electricity. Grade 12. Now we are able to conduct electricity. We've done something to this semiconductor which used to not conduct electricity. We have doped it, we have introduced an impurity to it, and this impurity has just brought instability to this semiconductor, making electrons move now, because there's a hole, and the electrons are now attracted from one place to another, and that movement of electron is the electricity. We can say that is electricity. So yes, we have made this semiconductor, okay, by doping it with a trivalent impurity. It's a trivalent impurity atom, such as aluminum. This atom could have been boron, by the way. Another example that we can use is boron for this atom that is impure. As long as it has a valency of 3, or as long as it is trivalent, it is going to bring about that instability, bringing this hole. It's important to know that there is a presence of a hole, which is a positive charge carrier. And since the positive charge carrier, it will then start attracting negatively charged electrons to it. Then the other one will leave a hole. Then it will also attract, leaving a hole somewhere else, also attract. So you end up having electrons moving from somewhere, having a sort of a movement where they are moving. And the movement of electrons, that's electricity, grade 12. Okay? Obviously, you would have connected it to some conductor for all of that to happen. Okay, now this semiconductor is no longer an intrinsic semiconductor. We can't call it an intrinsic semiconductor, because an intrinsic semiconductor was a pure semiconductor. What do we call this semiconductor now? Now, since this semiconductor comes with presence of holes, which are positive charge carriers, we are now going to call this semiconductor a p-type. P from positive charge carrier. So it's a positive charge carrier type of a semiconductor. It is a p-type semiconductor. This is a semiconductor doped with acceptor impurities, creating holes, such as aluminum, such as boron. Okay, if you take an acceptor impurity, you put it there and it creates a hole, that would be a p-type semiconductor. So now we know an intrinsic semiconductor, and now we also know a p-type semiconductor. We have done something to an intrinsic semiconductor, and that something is called what? Doping, adding impurities to it, right? And then we have added an impurity from group 3, and that impurity is trivalent. It has caused a presence of a hole, which is carrying a positive charge, or is a positive charge carrier, and that is making this semiconductor to start conducting electricity, grade 12. So in our hands there, we end up having a what? A p-type semiconductor. Okay, all right, let's see now. Let's continue and say, okay, what if then we have another one, right? What if instead of doping this silicon, we dope, instead of doping it with a group 3 element, we dope it with a group 5 element? Because we had 2 options, if you remember. We could dope with group 3 elements, which are trivalent. We can also dope with pentavalent elements, such as phosphorus or arsenic. What is going to happen, right? As you can see here, you have your silicon with what? 4 electrons in its outermost shell here. Okay, and then you have phosphorus. Phosphorus is pentavalent, which means it's going to bring how many? 5 electrons. Okay, then what happens? Then these 2 electrons will form a covalent bond. These ones will form a covalent bond. These ones will form a covalent bond. These ones will also form a covalent bond. However, now we have this guy here, which is an extra. So we end up having an extra free electron. Again, this is what we want. We have an extra free, emphasis on the word free there, extra free electron. Remember, the intrinsic semiconductor previously was stable. Everything was fine. They were, everyone had 8 electrons, right? Now, as much as everyone has 8 electrons here, we have an issue of a free electron in this case, okay? So what is the problem with this free electron? Say now, we take some power source, like I said, and we connect to this semiconductor. This semiconductor is not an intrinsic semiconductor. This semiconductor now has a free electron. What's going to happen here? This free electron is unstable, okay? It's free, it's roaming around. This free electron is definitely going to be attracted here because remember, it's negatively charged. So it's definitely going to be attracted by the positive charges of the power source. And this free electron is going to start moving. And remember, where the electron has moved, it will leave a positive charge carrier, a space. So wherever it is, it leaves a space. That space is attracting another electron coming in. And then that space attracts another electron. Then you end up having what? A movement of electrons moving all around, causing what? What we call electricity. So that means now we have a conductor in our heads. Remember, we said semiconductors are material with the electrical conductivity between that of a conductor and an insulator. So we have made a semiconductor to conduct by doing what? By doping it. By doping it with a pentavalent impurity atom. A pentavalent impurity atom such as phosphorus. And the semiconductor that was intrinsic was silicon. Okay? We can maybe do another one and say, what if we decided to dope with arsenic? Because arsenic is also pentavalent, to show you that we are not only going to dope with phosphorus or aluminum. So let's say we have our silicon. Silicon brings in those 4 electrons in its outermost shell. Silicon brings in those 4 electrons in its outermost shell. How do I know silicon brings in 4 electrons? From the periodic table, it's in group 4. So it should be bringing in those 4 electrons, okay? Then if I take arsenic, okay, which is in group 5, it will bring in about 5 electrons from the outermost shell. So what happens here again, you're now going to end up having a bond between the silicon and arsenic here. There will be another bond here between silicon and arsenic here, another bond here, then you will have another bond here. Then the same issue is going to happen here. You are having an extra electron. Okay, and you remember that electrons are negative charge carriers. They are negative charge carriers. Electrons carry negative charges. So what you have made here is a type of a semiconductor that carries negative charges, okay? And now you have an extra free electron that is roaming around. These extra free electrons is now going to do what? Conduct electricity, or is going to start moving. And the movement of electrons is the conduction of electricity, or is electricity itself. Great job. And again, as we've said, these are what? Are negative charge carriers. electrons, extra electrons that are going to be there. So we have a type of a semiconductor that is a negative type or negative charge carrier type of semiconductor. We call it the N. Where does the N come from? Comes from negative charge carriers that are being carried there. So it becomes an N type of a semiconductor. And we define the semiconductor as a semiconductor where electrons are charge carriers. And they are. And I want you to remember that we dope this one with what? A pentavalent impurity atom. Or you can just say a pentavalent atom. And we always dope an intrinsic semiconductor. We are always going to be doping an intrinsic semiconductor. So by looking at what we have done here, we started with an intrinsic semiconductor, grade 12, remember, which we made an example of silicon. It could have been germanium, but we made an example of silicon, right? It was intrinsic, and it was consisting only of itself, and we said it was stable because every other silicon was bonded to every other silicon, and every other silicon had 8 electrons and 4 bonds around itself, so everything was fine. Then we decided that we are going to do what? We are going to do a process of doping, which is adding of impurities to an intrinsic semiconductor. And then we said you can dope by using elements in group 3. Okay, we decided to use the element aluminum, doping the silicon by using aluminum. You remember aluminum is trivalent in group 3. So the 3 electrons that are there form bonds with other silicon, but create a hole with one of the silicon because it will not be able to form bond. It only can bring 3 electrons. That hole right there is what now starts this chain of electricity being conducted there. Okay, then same thing we did, and then we call that the p-type semiconductor, okay, because positive charge carriers by those holes. Same thing we do with the other one. Now we are doping with a pentavalent atom. What's this pentavalent atom? It could be phosphorus, like we used here. It could also be arsenic or any other one, but usually phosphorus and arsenic are the ones that are used. What do? They bring about an extra electron here. This extra electron introduces instability in this silicon that used to be intrinsic. It's no longer intrinsic now. There's instability because there's a free electron that is roaming around. So yes, other silicons might be happy forming bonds, but then there's a free electron. If something can take these free electrons, like the charges that are coming from the power source here, take it, it creates a hole, then electrons can be taken from anyone at any point. There's going to be a movement of electrons. Now remember, what I am showing you grade 12 here is a microscopic view of what happens, things that we cannot see with our naked eye. And I want you to remember that as much as or as big as I have made this to be, it happens at a very, very, very small scale, okay? And I have to say, right, in an N-type semiconductor, we are not only going to have one free electron or one phosphorus. It's multiple, so many, many phosphorus that are put there for doping. So it means if it's many, because remember you have many, many silicons in that silicon crystal. There is a lot, it's not just 4. I've used 4 to make you understand as to what happens, but there are a lot of silicon. A crystal will make something like this, where you have a lot. Think of these dots as what? As the silicon atoms, okay? This is even not enough of a depiction, but they are a lot. They are a lot. So that means when we are doping, we're also going to dope with a lot of phosphorus atoms, or a lot of what? Of aluminum atoms. That means we are going to have a lot of extra electrons. As much as I've used only one, I want you to keep in mind that there are a lot. So it's not only one electrons that is just moving, and now we're saying we have electricity. It's a lot of extra electrons that will be attracted by the positive charges in the power source, and then they will start moving there. And those electrons will then start creating electricity. Same case when we go to the p-type semiconductor. It's a lot of aluminums that are used for doping. And all those aluminums that are used for doping are going to create a lot of what? Of holes. I say this to say grade 12. Now I'm going to the next level now, because we have made a p-type semiconductor, and we have also made an n-type semiconductor. Now I want us to take it a step further and say, what else can we do? Yes, we've made a p-type semiconductor. We say now we can conduct electricity with a semiconductor that used to not conduct electricity. Okay, n-type semiconductor, we say it can now conduct, but what else can we do? Can we move a step further? And the answer to the question is yes, right? Question that we're going to ask ourselves is, what happens if we combine a p-type semiconductor and an n-type semiconductor? Say that we decide to take a p-type semiconductor, bring it closer to an n-type semiconductor, obviously through certain processes that will be taking place there. You're not just bringing them closer physically, through certain processes, right? We bring them together and we form a junction between a p-type and an n-type. What is going to take place then? Well, as I've said there, we are going to have something called a p-n junction, where we are combining. So we are having a p-n junction. That's when we are combining a p-type semiconductor, bring it together with the what? An n-type semiconductor. P-type semiconductor and an n-type semiconductor. Now I want you to look at this. Now look at how I have represented my p-type semiconductor. Now I've not represented it like I represented it before, where it had silicons and then there was one holes. Now I'm only interested in the holes. So I've only brought about the holes, right? Because those are the ones that are important. Those are the ones that are important for what? For the conduction of electricity. So we've brought the holes, and remember I said there are millions and millions or many holes that are there. Remember, we're not only putting in one aluminum, it's many aluminiums that we are using, or many borons, right? So we are going to have a lot of holes on the p-type. Same thing then. As you can see here, the white dot represents holes, the black one represents what? Electrons. Same thing on the n-type. On the n-type semiconductor, I have a lot of extra electrons, free extra electrons, right? Have to emphasize that, free extra electrons. They are many here because it's a lot of maybe phosphorus that was used there to create the n-type semiconductor. I want you to think of it like that, okay? Yes, I used only one. It was for explanation, understanding of what is happening at microscopic level. Now I want you to understand there's having a lot of holes, having a lot of extra electrons there. And then this is what is going to happen in a p-n junction. So what else happens now here? Okay, now since these holes here, we said these ones are positive charge carriers, right? If you remember, and you remember that electrons are carrying negative charges. Electrons are carrying negative charges, so they are negative. And you remember what happens with charges. Like charges will always repel each other, and unlike charges will always attract each other. You have to remember that from grade 10. So what's going to happen? So the electrons here closer to the junction, or closer to the midpoint of the junction where the P is meeting the N, right? These electrons will be attracted, and they are now going to migrate from the N-type going to the P-type. They are being attracted by the positive holes there that are carrying the positive charges. So these electrons, they what? They migrate. But then you would expect that all of these electrons should migrate until all of the holes right there have electrons. But no, that is not what happens, grade 12. So what you are going to get is that the electrons that are closer will be attracted, and then we'll take the holes that are also closer here, closer to the junction itself, closer to the midpoint of the junction, right? These electrons will go there, and then they will fill up these holes, okay? Unfortunately, they do not go and fill the first ones. It would have maybe been better if they went and filled these ones, and then these ones fill these ones, but that's not how it happens. They fill the first hole they see, and that's how attraction is happening. So they go, they fill the first holes that they see, they fill these holes. Now it starts looking like this, right? Because remember, they brought in the negativity here. So they go in there, and it starts being negative all over this place. Okay, Now, this does not mean these ones stop. They are no longer moving. However, they try to move these ones. As they try, they find these ones negative here now. And remember, when these ones left here, they left holes. So these holes became positive. That's why you're seeing them positive here. Remember, an electron leaves, and then it will leave a hole behind. Electrons move, an electron move, it will leave a hole behind. So they left positive holes here. Okay, these electrons that are here will also try to move, being attracted by the positive charges that are carried by the holes this side. So they will move trying to cross. But what is going to happen here is that these negative charges and the positive charges this side that have moved first will create an electric field. Okay, they will create an electric field. In these electric fields, these electrons will try to move. They will find the negative electrons that are here this side, and then they will get repelled by these electrons, and then they will move back. Okay, now we have a problem in this p-n junction that we have done here. Okay, seemed like it was working. Seemed like the electrons were migrating, going from the n-type to the p-type, moving all along, which was good and fine, and we were happy about it. However, now we seem to be having a problem now, because now these ones have simply moved, and then they've created a region here. And what is the name of this region? This region is called the depletion region. Region that has been created here. So they've created a region here where they've now ganged up on the all negative here, and they've left positive charges this side. Now, when these electrons are trying to cross and move across, they then repel them. You would remember again, like charges repel, unlike charges attract. Yes, they are attracted by the positive charges this side, but they cannot move past these ones, because every time they try to move, these ones, they push them back by their repellent energy. And this is happening in this electric field that has been created here. This causes a problem, okay? This is causing a huge problem, because now we are not having a flow of electrons. So whatever we have done by bringing a p-type semiconductor and an n-type semiconductor, then this is not conducting electricity for us. This is not good at all, okay? All right, so what can we do, okay? So before we can move to what can we do, what we have done, created the grade 12 by bringing an n-type and a p-type semiconductor. We have created something that is called a diode, okay? Our diode is not working yet. We'll look into it and try to make sure that the diode works. What is a diode? A diode is a device that allows current to flow in one direction, right? A diode is a device that allows current to flow in one direction. So that is a diode, grade 12. So that's the definition, okay? Okay, so let's forget this. We'll start here. We'll say a diode is a device that allows current to flow in one direction. That's the correct definition, okay? So there should be one here. It's a current that allows current to flow only in one direction. So in a diode, the current will only flow in one direction. It's not going to flow in a different direction. As you can see here, this is a circuit symbol of a diode. It looks something like this. This side of a diode, the one that is positive, it's called the anode, the positive terminal of a diode. And this side is called the what? The cathode. So, as it is saying, it is a device that allows current to flow only in one direction. So, current in a diode can only flow in this direction, going from anode to cathode. It cannot flow here. As you can see, here, this thing looks like a valve, okay? So, I always imagine this thing as what? As a valve that is stopping current from flowing from cathode to anode. Current can only flow from the anode to the what? To the cathode. So this is the circuit symbol of a diode. And this right here is the actual diode, how it looks like, or a typical diode will look something like this. And this is the microscopic view of what is happening inside this thing. As you can see again here, we are having those holes, right? We are having those holes and we are having these electrons here. And these electrons, they try to migrate, going to the other side. And when they do that, the first electrons that get there bring in these negative charges here, and then they leave positive holes this side. Okay, they bring in this negative charge, leaving positive holes this side. But these electrons are now trying to cross and go across. These electrons are now repelling them. Now we have that depletion region that we are talking about. That is now causing our PN junction diode not to work yet. Okay, let's say it is not working yet. Okay, so what can be done to make this diode to work? Okay, now we can now simply say, let's connect or conduct this to a what? An external power source, right? Like a battery. Let's bring in a battery, an external power source now. Why are we bringing in a battery? We have a problem of this thing here that we are calling a what? A depletion region. We have a problem of this depletion region here. This depletion region is stopping electrons from moving. We want electrons to move. Electrons must continue moving. Then we're going to say we are having a conduction of electricity. Electricity is being conducted. We have electricity there. So we bring in an external source, such as a what? Such as a battery. Now, if we bring in an external source, such as a battery, and then we connect this battery, right, such that the positive terminal of the battery is connected to the anode. You would remember, right? The anode of the PN junction. Remember, this is the PN junction. The anode is positive and the cathode is negative. So when you see this, this should be the anode, P-type. Okay, this is the cathode. So if I connect, or we connect, the positive terminal of our battery to the anode, this would be the anode, or to the P-type. Another way I remember it, I say connect the positive terminal to the P-type, so that it's PP, okay? And connect the negative terminal to the N-type, so that it is what? NN. Here you have PP. But the correct way for it is the anode is connected to the positive terminal of the battery. But you can remember it also as PP and NN, right? Okay, I'll tell you how that is going to help you later on. So you have a positive terminal connected to the anode, and then you have the negative terminal. We make sure that we connect it to the what? To the cathode. Okay, how does this help us? Well, you would remember, this battery now comes in with positive charges. Positive terminal, positive charges. Negative terminal, negative charges. So what happens is that these positive charges here will start attracting these electrons, pulling them. Okay, these electrons are now going to be pulled. Remember, these electrons, they were creating a depletion region here. So if something or someone then comes and pulls these electrons, they start moving, because their problem is that they were stuck here, they were not moving forward. So once they start moving, then they start allowing more and more electrons to do what? To move across from the N type. Okay, this will be the N type semiconductor to the P type semiconductor. That's the aim. We want electrons to be moving from the N type semiconductor to the P type semiconductor. And this way of connecting a battery is helping us, because now the positive charges are attracting the negative charges, which are electrons this side. Now they are moving across. Okay, and then we are having more and more electrons that are moving. And remember, these are the negative charges of the battery. These negative charges are moving like this. So more negative charges are being pumped in this side, more negative charges are being pulled to this side. So we are having negative charges moving like this. And once again, great help, we have negative charges moving, having negative charges moving like this. And once again, we have negative charges moving, we say we have electricity. Electricity is being conducted. So it means we have dismantled this depletion region here. that was causing electricity to stop being conducted. Okay, now we have a diode. Our PN junction diode is working because our problem was that our PN junction diode was not working. So we've made this PN junction to work by connecting it to a what? An external power source, such as a what? As a battery. Okay, let me talk about these arrows that are being shown here. These arrows here are showing the movement of the holes. You would remember that if these electrons are moving, then it means we are leaving holes here. So it means the electrons move in this direction and the holes move in this direction. You remember again that whenever an electron moves, it will leave a hole. An electron moves, it leaves a hole. An electron moves, it leaves a hole. So you can see that the holes are actually moving in this direction, while the electrons are actually moving in this direction. Okay, so we have ourselves a what? We have ourselves a diode that is working. We have electrons moving in this direction and we have holes moving in this direction. Okay, so what type of a diode is this? We call this grade 12 a forward biased diode. That's what we call it. It is a forward biased diode. A forward biased diode is a setup where the P type is attached to a positive terminal, PP, if you remember. So a P type is attached to a positive terminal, and an N type is attached to a what? A negative terminal, NN. So a negative terminal of the battery to the N type, positive terminal of the battery to the P type. So when that is happening, that will always allow for the flow of electrons. Now, let me make sure that we are not creating misconceptions here, grade 12. You would remember that when we look for the direction of current, we look for what we call, in grade 10 again, conventional current. So whenever they ask a question, what is the direction of current then? You can see that the electrons are moving like this. So we are not going to say the direction of current is like this. The direction of current moves through the anode to the what? To the cathode. Let me draw my circuit symbol again. This is my circuit symbol where you are having the anode and there we are having the what? The cathode. Okay. So whenever I'm explaining the movement of electrons, I know to most of you, it will start seeming like now the direction of current is moving in this direction. But you just said a moment ago, current does not move like this, or current does not move from the N type to the P type. Yes, it does not. Remember, when we look at current, we look at what? Conventional current. So current will move through the anode. The conventional current moves in this direction, through the anode to the what? To the cathode, okay? But the flow of electrons will move in this direction from the N type to the P type. I just wanted to make sure that there's an understanding of that and we are not causing confusion or misconceptions in that regard. So again, we call that type of a diode that we've just created there a forward bias diode. It is forward. It biases the forward. It favors the forward direction. It favors the conduction of electricity. So a forward biased diode, we always say the P type must be connected to the positive terminal. The N type must be connected to the negative terminal. Always remember that. PP, NN. Okay? Anything that is opposite that is not forward bias. Okay? So let's look at another type of a diode. What if we decide to say, okay, let's not do that. Okay? Let's rather connect the negative terminal to the P type. This is supposed to be positive and this is supposed to be negative. Okay, mistake here on my image. So let's rather connect the negative terminal and let's connect it to the P type. Okay, the positive anode, because it will still be an anode. Okay, this will still be a what? Okay, so let's rather connect the negative terminal and connect it to the anode. And let's connect the positive terminal, connect it to the cathode. Are we still going to have electricity being conducted there? Okay, in that case, we are going to run into a problem. Now, how so? Now, you remember that this is positive and we have electrons in the N type. And what is this positive going to do? this electron is just going to what? Attract, or these positive charges here will attract these electrons. So it means electrons in this case will just decide to move in this direction, attracted by the positive, right? And you remember here we have a negative or negative charges on this side of our battery or external power source, whatever it may be. Let's say it's a battery in this case, right? These negative charges are being pumped in. So it means we are having more and more negative charges. Remember, these negative charges have created a depletion region here, okay? So if we continue pumping more electrons this side, these electrons that were supposed to be moving like this cannot cross, right? We are increasing, okay, the depletion region. And when these electrons are being attracted this side, we are further increasing the what? The positive charges. So electrons cannot migrate and go through the other side. So we are not having a full loop of electrons moving. And remember, we are not having a full loop of electrons moving. So what happens then? Then we keep on increasing, because now these are negative, 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 negative. Okay, we increase the negative charges this side, we increase the positive charges this side. So we are having a what? An increase of the depletion region. So the depletion region will continue increasing in this diode of ours if we connect it such that the negative terminal N is connected to the positive terminal P. So if it's NP, right, and the positive terminal is connected to the negative type PN. So NP, PN, that is not going to work. So it means this diode is not going to be able to conduct electricity. So we are having what we call a what? A reverse bias diode. This is a setup where a P-type is attached to the negative terminal of the battery, and an N-type is attached to the positive terminal of the battery. Let's try and draw it in a sort of a circuit. You would remember this would be your cathode, negative, this would be your anode. Okay, if you decide to draw your circuit diagram such that the negative terminal is connected, you will not have a flow of electrons there, so you will not have electric current. Okay, you are going to increase the depletion region. The depletion region will increase, further increasing, causing more electrons to struggle to what? To go across from the N-type to the P-type. So you now have what is called a what? A forward biased diode. Okay, so grade 10, we are just going to simply take 3 minutes for an activity, and I want to see if you are understanding what we are doing here. I want you to do this activity where you draw a circuit diagram showing a forward bias diode, and then again draw a circuit diagram that is showing a reverse bias diode. I want to see your circuit diagram can have a resistor, a light bulb. You can add those things, or you can choose not to add them, as long as there's a diode that is showing forward bias and a diode that is showing connected in a reverse bias. Grade 12, your time starts now. Right, welcome back, grade 12. I hope you've tried our activity and I hope you are getting it right. So, I'm trying to help you draw a circuit diagram here showing a forward bias diode, okay? And then the second question was saying draw a circuit diagram showing a reverse bias diode, okay? So remember, if you are drawing a circuit diagram, you're not going to draw a PN junction like this one here, where you are going to draw holes, and then we are maybe going to draw electrons. Okay, this is not how we're going to draw it in a circuit diagram. Okay, we said the question is asking you for you to draw in a circuit diagram. Yes, this might be a PN junction diode looking at this, but we want it in a circuit diagram. So the expectation is that, well, you can even just simply start with the diode itself. All right, say here's the diode. Okay, the circuit symbol of a diode looks like this, and we want to connect it such that it is forward biased. Maybe you can put in a resistor or a light bulb here. So let's connect it such that it is forward biased. For us to connect that such that it is forward biased, we must connect the P type, which is the anode here. So we'll have our anode this side, and it must be connected to the positive terminal. And then you are going to have the cathode here, which is negative, and then it must also be connected to the negative terminal. So our simple circuit that shows a forward bias diode should look something like that, grade 12. Okay, and then for question number 2, draw a circuit diagram showing a reverse bias diode. Okay, I want to draw my diode facing like this, so that you don't start thinking that a diode will always face in this direction. So I want to change and draw it facing like this, but I want to draw the diode such that it is reversed biased. So I know this is my anode, which is positive. I know this side is my cathode, which is negative. So I am going to connect the negative terminal, right? Negative terminal, let's put in a resistor this time around. So we are going to connect the negative terminal to the negative terminal to the anode, okay? And also connect the positive terminal to the cathode, okay? Right, the negative terminal must connect to the anode, yes, and this one is positive, sorry about that. Okay, so the negative terminal connects to the anode, and then the positive terminal connects to the cathode, and this is showing us a what? A reverse biased diode, okay? Right, so I also want to show you pictures of circuit diagrams of forward bias diodes and also reverse bias diodes, okay? Your solution should look something like this. As you can see here, here's our diode, and then you have A here. Oh yes, and by the way, A is the symbol that is used to represent anode, okay? And then for cathode, the symbol that is used is K. K is used to represent what? Cathode, okay? So as you can see here, this is a forward bias diode, or a circuit diagram that shows a forward bias diode. Here's our symbol, or a diode symbol. You can see that the anode, this side A, is connected to the positive terminal of the battery. PP, as we said last time. P must be connected to P, right? And then there is a negative terminal, or there is the negative terminal of the diode, or the cathode in the diode, connected to the negative terminal of the battery, okay? And then, and here you have it here. Here's your light bulb, and it clearly says the light bulb is on. The light bulb should be on because you are having electricity here. This diode, which is a semiconductor, is now conducting electricity, okay? And this one is supposed to be reverse bias, okay, or reverse biased. Okay, so what's the difference between the two here? As you can see, they've written the symbol A here, which represents anode, and then K here, which represents cathode, okay, which is negative, and this is positive. So this anode is connected to the negative terminal of the battery this time around. The anode is connected to the negative terminal of the battery, while the cathode is connected to the positive terminal of the battery. This here, if we had a light bulb in this, the light bulb will not be on. So we'll say light not on, because we're saying light is on here. So light will not be on here because we are not going to be having electricity flowing through. In this case, it's a reverse bias diode. So we have a forward bias diode. We also have a reverse bias diode that we formed through a what? A PN junction, where we are combining a P-type semiconductor with an N-type semiconductor. We had a depletion region that was being formed here, but we took care of that by providing an external source, where if we connect it in a certain way, it will conduct electricity, but in a certain way, it will not conduct electricity. So this emphasizes what we defined a diode as. If you remember, we said a diode is a device that only conducts electricity in one direction. It only conducts electricity in one direction. So this device conducts electricity in only one direction. So if you connect it in this direction, there will be no electricity conduction, or electricity will not be conducted then. But if you conduct it in this direction, it will conduct electricity. So it only conducts electricity in one direction. So you must be careful as to how you conduct your diode. Okay, right? Let's talk about the direction of current flow here. As you can see now in a circuit diagram, I hope it's clear now. The direction of current flow is this direction, our conventional current. This is the direction of the current flow, going from the positive terminal to the anode, through the cathode, all the way to the negative terminal. But if you remember, the direction of electron flow is opposite. And all of these things are things that we have done in grade 10, grade 12. You remember that in grade 10, we talked about the difference between conventional current and electron flow current. So the direction of electron flow is in this direction, but the direction of the current is in this direction. In the diode, you're not going to have current flowing in this direction going through the cathode. It does not happen like in this case. You are going to be having current flowing like this, but this is not going to conduct, because as I always think of it like that, I think of it as if this is a valve stopping the electric current from entering if it comes in that direction. It only allows it if it comes from the anode. If it comes through the cathode, it does not allow it. Reverse bias diode, forward bias diode, grade 2. Okay. Right. Now, I want us to look at something that can summarize everything that we have done for the day, right? And this is what we call a characteristics of a diode. So what is the characteristics of a diode? This is sort of a graph that is used to summarize everything that we've spoken about here, or specifically the diode, all right, or the PN junction diode, because there are a lot of types of diodes that are out there, but we talk of the PN junction diode, the simple diode that is formed by a PN junction. So in this here, we're going to talk of a characteristic of a diode. What does the characteristic of a diode do? It is going to give us a summary of what is actually happening with our diode. Okay, so the characteristics of a diode will look something like this, as you can see right in front of you. Okay, this this graph is going to be looking at the relationship between current and voltage. Okay, I usually like writing it like this. For this one, I say I want to look at the relationship between the current and the voltage when the diode is connected forward biased. So for this one, it will look something like this. Okay, it will be connected forward bias. This is for the forward bias, this right here. So in actual case, I like it when we write IF for current forward and VF for voltage forward, to see we are checking what is happening with voltage. Remember, we said for us to be able to conduct electricity, remember we had the PN, the P-type, the N-type, and we had a PN junction. and that was that issue of what depletion region. Now, when we bring in an external source, that means voltage is going to increase. So as the voltage increases across this diode, what actually happens to the current? Okay, are we having current being conducted? Are we having an increase in the current? So let's look at it here. Okay, so we are having here, starting from 0, we are now having, saying voltage is increasing in this direction. So the characteristics tells us that the voltage will increase, but the current will not increase. Okay, so the current will not simply increase, right, as the voltage increases, until the voltage reaches a certain amount somewhere here. Then at that point, then you will notice the current just drastically increasing linearly, so meaning that now as the voltage increases, now the current increases almost at the same rate. But when you looked at this before this point here, as the voltage was increasing, the current was not actually increasing. It was almost constant in this case. It was almost constant in this case. However, it reached a certain point. What do we call this point? We call this point knee voltage. It reaches a certain voltage, and this voltage is called what? Knee voltage. So when the current or when the voltage reaches knee voltage, okay, knee voltage, this is the minimum voltage that is needed for the diode to start conducting electricity. So when it reaches knee voltage, well, the current starts shooting up, connecting or conducting electricity as it is. Knee voltage is also referred to as also cut-in voltage. So another word for it is cut-in voltage. So it can be called knee voltage. It could also be cut-in voltage. These are numbers for knee voltage if you are using a germanium for your semiconductor, intrinsic semiconductor. The knee voltage needed there is 0.3. Okay, and then the knee voltage for the silicon is 0.7 volts. Okay, that's the knee voltage that is needed. Not something that you should stress yourself about grade 12. You don't need to know that. What you need to know is that this voltage, the minimum voltage that is needed, is knee voltage. So you need to know its name. It's called knee voltage. You need to know that this is a what? It's also called the cut-in voltage. At this point, then the diode will start conducting electricity. Remember, start not conducting, it reaches knee voltage, then starts conducting. That's why you see this graph just simply increasing linearly in this case. Okay, so that's what happens in a forward bias diode. In a forward bias diode, you're going to have the diode not conducting electricity for some time until voltage reaches a certain point. You need to remember, this small conduction is probably happening during the creation of the depletion region. If you remember, in the creation of a depletion region, there's a movement of electrons. So this small voltage or small current, because it's not actually zero, but it's a small current that is here until we reach knee voltage. Once we reach knee voltage, current increases drastically and dramatically. So, great talk. Okay, so what happens in a reverse? What happens if we have a reverse bias diode, in which case the P-tap is connected to the negative terminal and the N-tap is connected to the positive terminal? This will be reverse. This is reverse bias, and then this is forward bias. Okay, so what happens in a reverse bias graph? Again, we are having here, I will call this IR, current reverse, and then we call this VR, voltage reverse. So what is happening there? Well, this one is going to just have just a constant current that is having them. Small current. Again, one might be asking yourself, why is this one not zero? Remember, we said if it is connected in reverse, it does not conduct electricity. Well, theoretically, that is the case, grade 12. It does not conduct electricity theoretically, but practically, if you do it practically and you measure, take a very sensitive ammeter and put it across this diode here, maybe put an ammeter here, you will read a small amount of current that is formed through the increasing of a depletion region. If you remember, we said there in a reverse bias diode, because of how the battery is connected, the depletion region will increase. So that means there are electrons that are moving across, but they are getting stuck. Not all of them are moving across, so the depletion region increases. So that small current that is happening with just a small movement of electrons, we call that the leakage current. It's the leakage current. It's sort of current is leaking. All right, if you want to understand, it's like there's a small current leaking there that is not supposed to be leaking. So it's called the leakage current. This is the current that is shown by the characteristics of a diode here. Small current, it's so small that it can be neglected. So we neglect it, and theoretically we just say there is no current at all because it's so small that it cannot even help to light a light bulb or whatever small component that we can use. It's very, very small and minimal. It is of no use at all. As you can see, for silicon, it is 20 microamps. 20 microamps, very small. Here, 50 microamps for germanium. Okay, and then this happens if you continue increasing the voltage across this diode. This current will continue there being constant, small, you increase until you reach this point. Okay, what is this point? This is when you have used too much voltage across the diode. So you have exposed this diode to a large amount of voltage. And what does this diode do? It breaks down. So it reaches what we call reverse breakdown voltage. Characteristics of a diode. We have knee voltage, the minimum voltage needed for the diode to conduct in the forward bias. In a reverse bias, we have reverse breakdown voltage. This is the maximum voltage. This is the maximum voltage that you can expose a diode to. So you connect a diode in a reverse bias manner and you expose it to a large amount of voltage, the diode is going to break down. And if the diode breaks down, obviously the diode then does what? Starts conducting, because now there's a large amount of current that does start suddenly flowing through the diode. But this current that is flowing through here is not good, okay? If in your circuit you have a circuit breaker, that's when the circuit breaker should come into play there now. Because this circuit breaker, this current that is now suddenly flowing here is not good. That's not the type of current that we want. The diode has broken down. So we are no longer having current flow because of the diode working. We are having current flow because the diode has what? Has broken down, which could be what? Dangerous. Why? Because you reach the maximum voltage that you can expose this diode to. This is called the reverse breakdown voltage. So you have the minimum, this side, minimum voltage that you can expose the diode to, or that you want to expose the diode to, for it to start conducting in the forward bias. But in the reverse bias, there is a maximum. There's a maximum. So you cannot say, I will keep on increasing the voltage. At some point, it will start conducting electricity. No, it's not. You increase the voltage, it will eventually come or reach a breakdown voltage where it will break down. So if maybe we're thinking, what if we keep on increasing the voltage even on the reverse? Won't it increase the depletion region to a point where it is now connecting electricity? It's not going to happen. You are eventually going to break down that diode that you are using if you connect it in a reverse bias diode. But let me emphasize on the point here. We say theoretically, we say it does not conduct electricity, and I want you to stick with that. However, practically, it does conduct a little bit of electricity, and we call that leakage current. So that's what the characteristic says about the PN junction diode. It sort of tells the whole story of what is actually happening. All right, so I want you to do this homework, grade 12, question 8 from one of the previous question papers, where you answer these following questions. They should be simple because questions in this chapter are relatively easy to answer. So today I have two questions for you. It's question 8 because it's only simple questions, question 8, and also question 7 from a previous question paper. So try to answer these questions, and if you understood everything that we are talking about there, it should be very, very simple for you to answer these questions as your homework. If you get stuck, you will then consult your teachers, and then they should be able to easily help you answer the questions. Okay, so in summary, you would remember that we wanted to say by the end of the day, we must be able to define a semiconductor, okay, as the material that has electrical conductivity between that of a conductor and an insulator. Define an intrinsic semiconductor, and then we say intrinsic semiconductor is a pure semiconductor. Define doping, a process of adding impurities to an intrinsic semiconductor. Differentiate between an N-type and a P-type semiconductor. An N-type semiconductor is a conductor that has been added impurities of or pentavalent impurity atoms, right? Where you add pentavalent impurity atoms, and in a P-type, that's when you add trivalent impurity atoms. Explain the construction and working of a PN junction. That's when you take a P-type semiconductor and N-type semiconductor, and then the electrons flow to the other side, creating a depletion region. But when you introduce an external source of energy in a forward bias, the electrons or the electricity is conducted. But if you do it in a reverse bias, it will not be conducted. So the diode, it shows the diode conducts electricity only in one direction. Then also interpret the characteristics of a PN junction diode. As we have seen in the previous slide there, the characteristics where it shows the relationship between the current and the voltage, where we need a minimum for the forward bias, the minimum voltage called knee voltage or cutting voltage for electricity to start conducting linearly. And in the reverse diode bias, we have a maximum voltage that you can expose the diode to, and we'll have a breakdown voltage there. So that's it that you needed to know for the day grade 12. Ensure that you join us the following week or on the 9th of May 2025, past 2 up until 4 o'clock, as we'll be tackling the topic of wave and sounds. Grade 12, good day.